So welcome to all. Myself Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Electronic Engineering. Today I am going to discuss about diode laser. Okay. So diode laser is a part of semiconductor optoelectronic devices. So before discussing the diode laser, I will try to discuss about some characteristics features of laser. So what is laser? Okay. So these are some outlines here. So what is laser? So the full form of laser. Laser stands for light amplification by stimulated emission of radiation. So light will amplify by stimulated emission. Means there is one phenomenon known as stimulated emission. Due to that, once the light will amplify, their intensity will increase, then such type of emitted radiation in the form of light will be called as laser. So that's why the laser full form is light amplification by stimulated emission of radiation. So a laser is a device that can produce a very narrow intense beam of monochromatic coherent light. So narrow intense beam of monochromatic coherent light. These are the characteristics features of laser. If laser light will produce, that laser light will follow narrow, means they will try to propagate in a unidirection, means their angular spread is very, very low. Intense means number of photon per unit available area in the path of that laser light will be too much high. That's why intense beam. Monochromatic, they will contain a single frequency. That light will contain nearly single frequency, and that light will be coherent in nature. So if laser light will produce, that laser light will have these features: narrow intense beam of monochromatic coherent light. But this is the full form of laser. If the light will come, or light will generated or amplified with the help of one phenomena named stimulated emission of radiation. Amplification means something will amplify, something will already present, and that thing will be amplified. Their intensity or amplitude will increase. So here in the case of laser, light will there, but that light will amplify by stimulated emission of radiation. So that thing is known as laser, and if laser light will produce, that laser light will follow certain characteristics, and those characteristics are narrow, intense beam of monochromatic coherent light. So, okay, so that things is written here. These things are characteristics features of laser, that is highly monochromaticity, highly directional, high intensity, and highly coherent. So monochromaticity means contain single frequency. Highly directional means if the laser light will emit, it will try to propagate in a unique direction, and their angular spread theta will be very, very small. Okay, high intensity means number of photon per unit available volume or area, depends on your consideration, will be high. Highly coherent. So coherent, I will try to specify the coherent. What is the meaning of coherent? So literal meaning of coherent is consistent, and that consistency will be measured in the term of phase. So suppose any two lights or any two waves are propagating in a medium. This is first wave, this is second wave, and at particular time t1, both wave have at each and every point x1, x2, x3, x4 have a same phase. Then these waves are known as coherent wave, and they follow the particular characteristics of coherence. These waves are having the spatial coherence. They are coherent with respect to space. At each and every point on a space, at any particular moment, they will have a same phase. Okay. Now, there are another type of phase that is known as temporal coherence. So, if this phase will match at particular time, not at overall space, means so see here, at this moment of time, if you record the picture of these two waves, so at this time t is equal to, let's suppose t is equal to t1, these both waves, first and second wave, have a nearly same phase. So these are, but all the point in space, they are not in phase. So at particular moment, these two waves are follow the same phase. So such type of coherency is known as temporal coherence. These waves will be in phase. They will follow the same phase with respect to particular time. Okay, or they will be in phase at particular moment. Okay, so if the laser will produce, that laser's light will follow such features. What are those features? High monochromaticity, high directional, high intensity, and highly coherent. And there are two types of coherence. First is spatial coherence, and the second one is temporal coherence. Okay. So I already told what is spatial coherence and what is temporal coherence. So here it is written what I told, what is spatial coherence and what is temporal coherence. Now, just I told what is laser. So some light will be amplified with the phenomena of stimulated emission of radiation. So what is stimulated emission? Okay, so before understanding or before the knowing to what is stimulated emission, we have to know what is absorption and what is spontaneous emission. Then it will be easy to understand what is stimulated emission. So generally, if you consider any kind of material, okay, at their normal condition, all the atoms of that material will be reside in their ground state energy. Okay, let's suppose these are the available energy levels for those materials, and I categorize as a E1, E2, E3, E4, and so on up to En. So all the available electron will be generally reside in their ground state energy. Okay. But if that material will be exposed by some sort of energy, like light or heat, okay, or any mechanical energy, what happens? These electrons will acquire the energy from that external source and and if that energy is sufficient enough so that these electrons can reach to their higher energy level, so that electron will jump to their higher excited state. Means, and what are here the available higher state? E2, E3, E4 up to En. So if it depends on the available exposure energy. So if that energy is very, very high, that outer energy, and that energy will be incident over these electrons will try to jump even in their too much higher state like E4, E5. But if there are even a small amount of energy, sufficient small amount of energy, and if that energy will incident over these electrons at least jump to their next excited state, that is here E2 or E3. Okay. So what happened? Now electrons are reach here, are here. So these electrons will not reside here permanently. They have to return to their ground state level. Up to what period of time? Up to 10 to the power minus 8 second period of time. These electrons will again return to their ground state energy E1. This is the phenomenon. So this process, by absorbing the external energy by these ground state electron and reaching their self to their excited energy, is known as absorption. Okay. So let's simplify these things, and I will consider only two energy levels, E1 and E2, for sake of simplicity. Now one electron is here. Okay. Now this electron is exposed by one energy E1, one outer source energy, from one outer energy source E1, and that source have energy E1, and that energy E1 or let's suppose E0 or some, because E1 E2 I already taken, so let's suppose EQ. Okay, that external energy source have the energy value EQ. Now that energy is absorbed by this ground state electron. Now what happened? If this EQ is greater than E2 minus E1, means if this EQ energy value is greater than this energy difference, available energy levels value energy difference, then what happened? This electron will jump to their excited state, means available excited state, and here that is E2. Okay. So this phenomena, absorption of energy by ground state electrons and reaching themselves to excited state, is known as absorption. Simply absorption. Absorption phenomena. Electron is absorbed some outer energy and excited to its excited level or higher energy level. That phenomena is simply known as absorption. Okay. Now what happened? This electron will not reside here permanently. They will maximum stay here up to 10 to the power minus 8 second. Means lifetime of these levels, this level, if this level are normal levels. Why? Because there are concept of metastable state. That's why I am telling if these levels are normal level. So the electron can reside here up to 10 to the power minus 8 second. And after that period of time, they will return to their ground state energy. And while returning time, they have to lose their energy. Then only this electron can reside again or acquire again the E1 energy level. Here its energy is greater than E1. Now this electron is now reaching here, approaching here, E1 energy level. So they have to radiate a sort of energy. Okay. And if this radiation will fall under the visible region, you will see this radiation in the form of light. Okay. So again they have to emit same amount of energy, EQ. And if this EQ energy or frequency, energy frequency will be fall in the visible region category. This EQ will be appear as a photon, as a light. Okay. So this phenomena, generation of energy level after absorption, is known as spontaneous emission. Okay. So see here, one electron is its ground state energy, and one sort of external energy is exposed this electron. Now electron jump to their excited state. After 10 to the power minus 8 second of period of time, this electron again returns to their natural energy level, means ground state energy level, and while returning time, this electron emit a kind of photon. And this photon energy will be always equal to the difference of these energy levels. Let's suppose this is E2 and this is E1. So this h nu emitted photon energy will be always equal to E2 minus E1. Now you have one photon, and anyhow, if this photon will amplify, you have one photon, and if there is any process exists in this nature, so that process will amplify the number of photon, then what happens? You will get the kind of intense radiation, amplification of light. Okay, so that is what I am going to tell in next. That is that process which will be available for amplification of light, and that phenomena, that concept will be always used for generation of laser light. And what is that phenomena? Remember this state. This state is important. Now this photon is generated, and if you are taking even a small amount of material, there are number of electrons will be present there, and it is not possible so that at any particular moment of time all electron will jump to their excited state. Okay, so some electron will go if those electrons will exposed by some external energy. So some electron will only go for their excited state, and some electron will reside their ground state. In next instant, whatever the electron will be reside in their normal state, that electron will again move or try to get a upward transition or try to move their excited state, and whatever those who are already in excited state try to do the downward transition by emitting the photon. Okay, so now this photon is available. Now next instant of time, let's suppose this is T1, this is T2, and this is T3 instant of time. Now this photon, this available photon, which is generated by kind of spontaneous emission, will hit this any excited electron. Means this is a kind of electron which are available in their excited state. And for this electron, this period of time, 10 to the power minus 8 second, is not happened now. After that, it will automatically decay. But before 10 to the power minus 8 second, if this electron, this emitted photon, h nu, which is generated by a kind of spontaneous emission, will hit this excited atoms or electron, this electron will decay to their ground state. And here you have to remember this phenomena will happen before the 10 to the power minus 8 second. Means now let's suppose now at this T3 time, this electron reach to their excited state, and after T3 time and after T3 time, the 10 to the power minus 8 second, before the 10 to the power minus 8 second time interval after T3 time, if any such type of photon will incident over this excited electron, this electron will again decay to their ground state before 10 to the power minus 8 second. Why this is important? Because after 10 to the power minus 8 second, this electron automatically decay. I am not taking that phenomena. I am considering that phenomena before 10 to the power minus 8 second time interval. If that photon which are available by the phenomena of spontaneous emission, if that photon will hit this electron will again decay. And while decaying, this will generate one again new photon. So now this phenomena will produce two photons. One is this stimulating photon and one photon is now available by this decay mechanism. So when such phenomena happen, means if the electron will go to from their excited state to their ground state before the 10 to the power minus 8 seconds, such type of thing will happen by kind of stimulated emission. Okay. And whatever the photon will generated by this phenomena is known as stimulated emission photon or simply stimulated emission. Okay. So now one photon is responsible for generation of two photons. Actually, it is initiated by a single photon, and as a result you are getting two photons. Now what happened? Your intensity of light is increased. Now this photon will again hit any two excited atom and they will again generate two additional photons. Now these two photons will converted into four photons. Now these four photons will responsible for generation of 8 photons. Then again 8 photons will responsible for generation of 16 photons. Now see, your number of photons is rapidly increasing. Means light is amplifying, and your laser name light amplification. By stimulated emission of radiation. So light is amplified by stimulated emission, and when these phenomena will occur, then the laser light will produce. Okay, why? Because whatever the photon will generated, that photon will follow their parent photon characteristics. Means, let's suppose this is the parent photon and that photon will incident over this excited electron. That excited electron will decay and generate one new photon. So that new photon and that parent photon will have a same characteristic. Means they will try to move in a unique direction. They will be in phase. And why? Because they are rapidly increasing their number. They will be able to maintain a high intensity. Okay. And they will have a same frequency. Means monochromatic in nature. They will try to move in a unique direction. Means in what direction this photon will go, this emitted photon will also follow the same path. Means they will travel in a unique direction. So that is the characteristics of laser. What is the characteristics of laser? See here, high monochromaticity. So all the photon will have a unique frequency, means highly monochromatic, highly directional. All the photon will now travel in a unique direction, is highly directional, high intensity, High intensity means what? Number of available photon per unit volume or area will be more. So now you will see they are rapidly increasing their number, amplify their number, means high intensity will come, then highly coherent. Obviously they will be in phase. Okay, they will have a similar kind of frequency, they will be in phase, so they will maintain a coherence nature also. That's why stimulated emission of radiation is important for generation of laser light. Okay, so these are some differences between spontaneous emission. This process is spontaneous emission process. This first one is absorption. The second one is spontaneous. It happens naturally. Spontaneous emission. And this third one is stimulated. Stimulated by one spontaneously emitted photon emission. So this stimulated emission is important for getting the laser light. Okay. So these are some difference between spontaneous emission and stimulated emission. And remember that why I am discussing all, because I want to deal with laser diode laser. Diode laser is a kind of optoelectronic device. And I am dealing the semiconductor optoelectronic course. So before discussing about diode laser, I want to discuss some basics about laser. Okay, so these are some difference between spontaneous emission and stimulated emission. So I already discussed, but let's see. Spontaneous emission take place when excited atom make a transition to lower energy level voluntarily without any external stimulation. It will take naturally. This transition will take a place naturally. Okay, but in the case of stimulated emission, take place when photon energy equal to the difference between two energy level stimulates an excited atom to make a transition to lower energy level. So I already discussed this one. Now, spontaneous emission may be polychromatic, means more than single frequency. The number of available photon will have more than single frequency. But whatever the photon will be generated by the process of stimulated emission, they will have a unique frequency. That's why such type of radiation will be considered as a monochromatic radiation. Now, less intensity. Spontaneous, whatever the photon will produce by spontaneous emission process, their number will be, available number of such photon per unit volume or per unit area will be very, very less. But in the case of stimulated emission, that available photon per unit area or per unit volume will be too much high, very, very large. That's why highly intensity. Less directionality, they will try to travel random in space. Means they can try to travel all the available direction. But these photons which are produced by a kind of stimulated emission phenomenon, they will try to travel in a unique direction. That's why high directional light you will get by stimulated emission. In the term of coherency, maybe they can maintain a temporal or spatial coherence in spontaneous emission also. And in stimulated emission also, they will obviously maintain the spatial and temporal coherence nature. But see, whatever the characteristics of laser, whatever the light generated by stimulated emission, that light will follow the characteristics of all the laser. So you can say that the laser can be only generated by stimulated emission. And this is the example of laser light, which occurs by the phenomena of stimulated emission. And any ordinary light source, you can say that, are generated by spontaneous emission. And there are one more concept of metastable state. So what I told, generally the lifetime of excited electron in any normal excited state will be 10 to the power minus 8 seconds. But there are the case where some levels will exist, they will have a lifetime greater than 10 to the power minus 8 second, means from 10 to the power minus 3 second to 10 to the power minus 6 second, because negative power. So they will show the higher lifetime. 10 to the power minus 3 will be greater than 10 to the power minus 8, or 10 to the power minus 6 is also greater than 10 to the power minus 8 second. So there are some state, there are the possibilities so that any levels can have the lifetime greater than 10 to the power minus 8 second. And if such levels will exist, then those levels are called meta-stable state. Okay, and existing of meta-stable state is very, very important for getting the laser light. Okay. Now, how you will get the laser light? Laser light will only produce by stimulated emission. Okay, and for phenomena of stimulated emission, number of available electron in excited state should be more, then only you can get the intense laser beam. Okay, so if the any available state where the electron can reside there from their normal lifespan, longer than their normal lifespan, so you can say then there is the chance so that the electron will photon will be emitted by stimulated emission. Okay, so for producing the meta-stable state, that's why for generation of meta-stable state anyhow by doping or due to some any effect is important for getting the laser light beam. Why? Because laser light will be only generated by the stimulated emission, and stimulated emission only happen from those electrons which are available in their excited state. So if there are the chance so that the available number of electron in their excited state will be more, then you will get the intense laser light. Okay, because the lasing action will be prominent. Okay, so one more concept is interrelated with this meta-stable state, and that is known as population inversion. So what is population inversion? Population inversion is the case where the number of electron available in their excited state will be greater than the number of electron which are reside in their normal state, ground state. So let's suppose there are two levels, E1 and E2, and normally the total available, let's suppose the total available in normal case, in their normal condition, the total number of available electron is N1. Now what happened? This system is exposed by any external energy source. So some electron will go to their excited levels and some will be still there, remain in their ground state. So now let's suppose these numbers are now in this case N2 and N3, where N2 plus N3 is equal to N1. Now anyhow, if such condition is maintained where N3 will be greater than N2, okay, means number of available electrons in excited state is now greater than the number of electrons in their ground state. So such condition is known as the phenomena of population inversion. So with the help of meta-stable state, you can achieve the phenomena of population inversion, and while achieving the population inversion condition, you can get the light. There are the more chances so that you can get the light or photons or laser light by the phenomena of stimulated emission. So these two things are interlinked, metastable state and population inversion. With the help of metastable state, you can maintain the population inversion condition, and by maintaining the population inversion condition, you can achieve the stimulated emission radiation, and that stimulated emission radiation will generate the laser light. So these are some lasing action phenomena where see the some sort of material which is exposed by photons. Now photon is going for their spontaneous emission. That spontaneous emission photon is now stimulating the stimulated emission, and that stimulated emitted photon is now traveling in unique direction. While traveling, they will again doing the phenomena of stimulated emission, means their numbers are increased. See here 2 photons, but in the next step 3 photons. Here kind of partially reflecting mirrors are present. So by incident over this partially reflecting mirror, these photons reflect back in this system, and again they will do the same phenomena, means they are increasing their number by stimulating emission process, and they will traveling in a unique direction and reaching to this end. This end is fully reflecting end, okay, a kind of mirror. So they will again reflected back by this end and again traveling in the same media and increasing their number by stimulated emission process. So all the spontaneous emission, absorption and stimulated emission process simultaneously take place. We have to focus only stimulated emission kind of thing. So see here, while traveling back and forth direction inside the medium, they will rapidly generate or increase their number. Once their number will reach to certain level, they will come out from this end. Why? Because this is the partially reflecting end. So some part will be reflected, some part will come out, and these outcomes light will be your laser light. Okay, so these are the phenomena, or these are some process, and due to that you can get the laser light, and these are the lasing action or lasing mechanism. Okay, so that's all for today's video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.